Okay, so today we're going to be looking at the domain, the range, the graph of logarithms and logarithmic functions, and then also looking at some of their cool applications as pertains to acidity and ion concentration, pH, orders of magnitude, dealing with huge and small numbers, and comparisons of huge and small numbers, and also things like the intensity of sound. So again, I said this earlier that logs really help simplify and make sense of quantities that are gigantic or really, really tiny. And that's because they invert exponential functions. So things that are many powers larger than numbers we can hold in our hands, so to speak, they work really well. So let's begin with domain, range, and graph of logs and how that looks. So if we want to have log functions in our toolbox of something we can model the real world with, right? So we're building our library of functions, then we need to know what the domain and range are on the what we call the short run behavior and the long run behavior. Because what the domain and range really are is what are we able to feed this function and what does it spit out, right? And what it spits out is obviously going to be dictating its shape, the things in the real world it can model, and the domain is again what we're allowed to input. So if we recall quickly exponential functions, what the domain and range of exponential functions were, take a moment to think yourself and recall what this might be. The domain, what are we allowed to input into this function? Well, we're allowed to input anything we want, right? Or all real numbers. There's no problems inputting a value into x. We can raise b to whatever power we like. And we know that this function is defined for all real numbers. It stretches infinitely into the negative values and infinitely into the positive values to the right. So let's just kind of sketch a graph to remind ourselves what this looks like, a tiny one up here. Here's my axes, and then my function does something like this, passing through that vertical intercept of 0a. I know that's tiny, but we just need kind of a rough idea of how an exponential function looks. So that's the domain. The range, again, is the set of outputs. And we should say a set of all possible outputs. So what is possible for this function to have as its output? Remember, that's on the y-axis, so what values are possible? Well, it's going to be all values that are greater than or equal to 0, and not including 0. Right, so we see that all y values are going to be stuck between 0 and positive infinity, right? Because we're talking about just these values up here, and it doesn't go beneath. Why is that again? Because you can't raise anything to a power and make it less than 0. Okay? Try to do it on your own in your calculator. It's not possible. We remember that. It has a horizontal asymptote at y equals 0. So this was for exponential functions, right? So why would I take time to talk about that? Well, how are logs and exponential functions related? They are inverses of each other. So the domain and range are actually going to be the inverse, that they're going to be flipped for logs the way they are for exponential functions, meaning the domain is going to become the range is going to become the domain. So let's see what I mean here. So for y equals log x, or y equals natural log of x, or really, we can have this for any base ax. These properties will hold up. We'll try to keep it general. the domain of what's allowed, possible inputs, what's allowed here to go into this function. Well, since it's the inverse of exponential functions, then anything greater than 0 will be allowed for inputs. So we could also say, or all non-negative. Actually, since we're not including 0, we should say all positive real numbers. Okay, so notice we're excluding 0 here. So that means that the natural log, or the log of 0, or natural log of 0, or log base a of 0 is undefined, or does not exist. This is kind of a key idea. So I don't want to box that in because this is really the domain. But this is a key idea here, that the log of 0 is undefined. Again, think about it. What does the log mean? It means this is the power of the function, power of the base that gets you 0. What we saw over here, can you raise a base to any power and have it equal 0? No, it can get infinitely close, but it will never get there. So log of 0 is undefined. So the domain here is all positive real numbers. And so the range then you can expect is going to look like the domain of the exponential function, which is that all real numbers are possible outputs. Right? If you think about this function, how it spans across the entire x-axis, this function is going to span across the entire y-axis. And let's sketch the graph and see how it relates. So the graph of a log function will look something like this. X and y axis here, passing through the point 1, 0, so on the x-axis. And you'll see it does not cross this x equals 0 or the y-axis here. Right? This serves as a vertical asymptote. It will get closer and closer and closer, but never really touch the y-axis. And up here it will increase, although it's going to be growing slower than you see. Right here we see some explosive growth, and over here it's more gradual growth. But this will continue to increase, albeit slowly, up to positive infinity. And so I want to draw a parallel here and show you, right, remember the exponential function. And we can say that this is the natural log function, and then this is y equals e to the x. What do we notice about these two things? They look very, very similar. They look almost symmetrical, not about the x or y axis really, but actually about the line y equals x. And this is a characteristic of functions that are inverses of each other, that they're reflections across y equals x, which should make some intuitive sense, right? That if we're swapping inputs and outputs, right? We're saying the domain is now the range is now the domain for this new function, that we would be reflecting across this line that we call like the identity of y equals x, or that mirror of the inputs and outputs. So that's pretty cool. So for y equals e to the x, it crosses through 0, 1. It goes off to positive infinity. It has a horizontal asymptote at y equals 0. And the log function translates that to being a vertical asymptote at x equals 0, but it also increases, we say, without bound towards positive infinity. So we see the range we see the domain here. Set of all possible inputs does not include 0, right? And this is going to work for all log functions. Now, depending on the base of the logarithm, whether it be 10 or some log a, that will change the shape of this graph slightly, but it will still pass through 1, 0. And again, the base is just going to change the shape of the bend, just like it would with an exponential function, right? 2 to the x looks different than 10 to the x. Same thing is true for logs. It's just going to be the mirror image. So this is what the graph looks like. Again, we want to maybe name out some asymptotes here. Asymptotes for y equals log x. We see that we have a vertical asymptote at x equals 0, or the y-axis. All right, now this can be shifted when we get into shifting functions, but the base functions, right, or the vanilla functions, just like this, are set with a vertical asymptote of x equals 0. And again, it's because of that input issue we have. We can't raise anything to a power to get it to be 0, so then we can't have that logarithm of 0, since that power can never take it there. So we have vertical asymptote. Question is, do we have any horizontal asymptotes? So does this function in blue look like it's going to level off and assume one constant value? Well, no, it's not going to happen. Down here, again, we said it's going to decrease to negative infinity. And up here, it's increasing without bound to positive infinity, right? It's going to keep going up. It's not going to settle to some value. Even though it looks like it's getting slower, it is concave down. We'll talk about that in a second. But it does still increase without bound. So there are no horizontal asymptotes. And again, this should make sense because there were no vertical asymptotes for exponential functions. So that means that there would be no horizontal asymptotes for logs. So a quick note here on, again, reusing limit notation, which is a big component of calculus. What this says is, as in English, we'd say as x approaches 0, y approaches, or f of x approaches negative infinity. That's what it means to have this vertical asymptote. And so with limit notation, what we would say is that the limit as x approaches 0 from the right, and we should put that here as well, of f of x, you could say equals negative infinity, but really what we'd say is does not exist or diverges to negative infinity. So again, Mally, why can't we just say this equals negative infinity? You kind of can, but really to say something equals infinity is conceptually pretty fuzzy. Infinity is not really a number, so we can't have something be equal to it. What we can say, though, to be more descriptive, is that we say it diverges to negative infinity. But for terms of like putting it into software and things like that, you can use DNE or just negative infinity for the entry. And again, for horizontal asymptotes, there are none, so we don't need to use limit notation there. But again, this is how we translate from these talks about long run and short run behavior. As x approaches 0 from the right, comes down here, and then this part talks about the output, so that's over here. You may not have seen this one-sided limit notation before. And it just means to approach from one direction. So for this here, this means approaching by taking values from the right of 0. So we might start at 0.1, 0.001, 0.01, 0.001, 0.0001, etc. See how I'm starting with positive values, or values that are greater than 0, and approaching 0 by getting smaller and smaller. So this is what it means to be a one-sided limit from the right. So while we're here, what would it look like to say x approaching 1 from the left? So what's a number that's smaller than 1, but we can get closer and closer to 1 without actually hitting it? So we might start at like x equals 0.9, 0.99, 0.999, something like this. Same with approaching 0 from the left. What's something that's less than 0 that I can approach with? So if I had negative 0.1, negative 0.01, you see how I'm moving to the right now on the number line. So if you just think about being on the number line, this is approaching from the right and this is approaching from the left. Okay, so this is how we'd use limit notation to talk about the long run behavior or the asymptotes. Okay, one last note while we're talking about the shape of this thing, and then we'll get into some cool applications, is the concavity of it. So again, what do we mean by concavity? We mean the bend of a function, which is determined by how the average rate of change changes. Okay, so if we take a look at a log graph, doing something like this, you want to think about, maybe this will help with the ruler, think about what's happening with the average rate of change. Well, what's the average rate of change again? Delta y over delta x. It's the slope of the secant line, we say. And the secant line just means that it intersects the curve in two spots. So we're looking at something like this. Here's a point, and then this slope here is your delta y over delta x. It's like the pitch of the graph. And we see, okay, that's pretty steep and positive, right? Reading it from left to right. And as I move these 2 points, maybe I'll use a couple 2 points here and here, I find the slope of the secant line there. Here's my new delta y over delta x. We see that the slope is less, right? What's a zero slope? Zero slope is horizontal. Very steep slopes have high values. Very steep slopes left to right like this going down have strongly negative values. So, if we make some stuff up, we'd say, okay, this looks like a slope of positive 10, then this would be like 8, right? And then from, how about here to here? Assuming we're keeping these x distances somewhat equal. Again, here's my delta y over delta x. This compared to, I didn't draw my straight line. This compared to the yellow, if this was an 8, this might be a 7, right? And so what do we notice is happening as we keep going? That the slope is, and you can see the angle here, right? Going down towards 0 degrees. Kind of an analog idea that over time, this slope is shrinking. So if the average rate of change is decreasing as x approaches infinity, or is, let's just say this a little bit more in plain English, as we go left to right, thus the log function is concave down. And it makes sense that it's concave down, or it bends down, and again, it's key that we're reading graphs left to right. It makes sense that it bends downward because what way does the exponential function bend? If you remember the exponential function, something like this. What way is that bending as we go left to right? Yeah, it's bending upward. We see slope from here to here. Oops, we see the slope from here to here versus the slope from here to here. It's getting steeper. All right, so if this was like a 3, this would be like a 5, this might be like a 9. Again, I'm making these numbers up, but you can see the slopes are certainly increasing. The pitch of that roof is getting steeper from left to right, and this is concave up because the average rate of change is increasing left to right. So it makes sense that since the average rate of change is decreasing with logs, that it would be concave down. Okay, so I'm kind of over-explaining this idea, but I feel like concavity is something that isn't discussed enough, and it's really important. It tells us what's happening in a kind of a second-order analysis of how something's changing, right? So you can look at log and say, yeah, this function's increasing, but another kind of next level analysis of it would be to say it's increasing, but the rate at which it's increasing is slowing down, right? So what does that tell us? Well, I mean, we're all pretty well versed in what do we call it? Flattening the curve, right? We understood very, very clearly what flattening the curve meant in 2020. And so that was a second order analysis. We're talking about the concavity of that logistic function of the spread of the virus and the number of cases and the number of deaths. We know that that rate of change is something that we wanted to decrease. So anyway, concavity, obvious real world importance, and in general, right, for many functions, talking about how the average rate of change is changing. We do a lot of that in calculus. So you should be at this point pretty familiar with domain of log, the range of log. Again, this is for the vanilla version, unshifted, unscaled, unstretched. Passes through 1, 0. It has a range of all real numbers, what its asymptotes look like, this limit notation, and then again its concavity. So we've got all these general properties, and now let's jump into a few examples of how we use log in practice, something that takes these giant numbers and shrinks them down to something more manageable. So we'll first look at chemical acidity. So, those of us, and myself included, with very limited knowledge of chemistry, just a quick review that we measure acidity by using something called pH. And it's an index to tell us how acidic something is, so we can compare, water to battery acid to soap to different things. And what this really represents is the concentration of hydrogen ions. This number is typically measured in moles per liter. It's a range from 0 to 1, but we map that to this index called pH, which again tells us how acidic something is. 7 being truly neutral water. So the relationship between pH and hydrogen ion concentration, which again this is the actual concentration of hydrogen ions, is as follows. We know that the pH is given by the negative of the log of the hydrogen ion concentration, and we use this H plus in brackets to represent that. So this is the formula we'll use for problems like this. And again, a equation is a two-way street. You will hear me say that a lot. So we want to be able to go both ways on this equal sign. So let's think of something right here in front of me is a cup of black coffee. And I happen to know this has a pH of 5. So I'm going to ask a couple questions about this. Question 1, how much more acidic is coffee than water? And question 2, I'll ask what is the hydrogen ion concentration of coffee? So let's start with question 2 first. I know that black coffee has a pH of 5, so if I'm trying to find out what is the hydrogen ion concentration, I can use this equation, pH equals negative log of H plus. And so that means that 5 is equal to negative log of H plus. And this is, again, common logs. This is base 10. So what we can do here, there's a few ways to go. What I would recommend is multiply both sides by a negative 1 to strip this negative sign off of the right-hand side and bring it to the left. So we get negative 5 equals the log of H plus. And then how do we free the H plus from being inside the logarithm? We use that property that we used in the last section, which is raise both sides as powers of 10, right? If A equals B, 10 to the A equals 10 to the B. And we're using base 10, so that we get 10 to the minus 5 equals, well, 10 to the log of something is just that something. And so we see, okay, 10 to the minus 5 equals H. Plus we could leave it like this, or say that this is equal to 0.00001 moles per liter for black coffee. right? Because we have 1, 2, 3, 4, 5 decimal places backwards. So logs doing their thing of helping us take tiny numbers and bring them more kind of into our hands with something like 5, right, being the pH. So that's the hydrogen ion concentration of black coffee. Now the question is, how much more acidic is coffee than water? So what we want to do is, well, we know the pH of water is 7. It's truly neutral. It's not acidic or basic. So we know that 7 must equal negative the log of its positive ion concentration, which is really what's being measured here. So the acidity is determined by this H plus value, so we want to compare those two. So what we can do is go ahead and solve for hydrogen ion concentration of water. And so again, we'll get negative 7 must equal log of H plus, and then we'll take 10 to the power of both sides and see that the hydrogen ion concentration of water must be 10 to the negative 7th. So when we want to compare these two quantities of coffee, we know that coffee was ion concentration of 10 to the minus 5. How do we compare these two, or how much more acidic is coffee than water? Is the question. What we might do as a side thought, if we're comparing two things, say, the price of a house versus the price of a bicycle. Why do I choose these two things? Well, because a house is way, way more expensive than a bicycle, but we want to compare these two quantities. What I might do, instead of just showing the difference between the two, is I might show the ratio. Right, so I might show that I have a $100,000 house versus a $1,000 bicycle. And what do we get? We get 100 over 1, or just 100. So we'd say that, the house is 100 times more expensive than the bike. So use this idea of a ratio. Same thing's going to be more helpful when we're talking about powers of a base, right? Powers of 10 or powers of E. We'd rather talk about ratios than talk about a linear difference, or just subtracting the two things, because those are going to be very, very small. So if I compare then the ion concentration of coffee to water, and I say, all right, we have coffee to water, and I take this ratio, which is 10 to the minus 5th over 10 to the minus 7th. 10 to the minus 7th is a smaller number. Make sure you understand why that's the case. Think about what that number really means. And so when we divide these two to come up with this ratio, what we'll actually get is, if you remember your exponent rules, right, 10 to the minus 5, we subtract what's being divided by, and so we'll actually get 10 to the 2, 10 to the positive 2, which is what? 100. So this means that coffee is 100 times more acidic than water. as I sip on this coffee, that's a pretty crazy thing to consider. But all joking aside, this can be a method of comparison between the acidity of different substances, and their pHs don't have to be these whole numbers that I've given. It could be a pH of like 4.61 and 6.98. The same process will hold up, and you can still talk about how many more times something is acidic than another, right? Or just like the same way, how many more times something is more expensive than the other. It's an awkward sentence, but I think you know what I'm talking about. So that's all I'll say for chemical acidity. Again, remember you can go both ways on this equal sign to talk about concentration of ions in the solution as well as the pH index. And now let's work into looking at sound intensity. Okay, so another cool application is sound intensity. What's audible in terms of sound and the frequencies of sound is a huge range. And what do logs do? Logs squish huge numbers. Or rather, they squish huge ranges of numbers. So measuring sound intensity is a natural application for logs. They take the whole real line and squish it into a smaller range. So because of its slow growth. So what we do typically is we measure intensity of sound in relation to a benchmark. Since it's such a huge range, and we use this notation I naught or I sub 0, which is the sound intensity that's barely audible to most humans. And so this intensity is 10 to the negative 16th. It's measured in watts per centimeters squared. And again, what we typically do is we compare the intensity of other sounds in this kind of a rough unit of energy per surface area units. We measure whatever we're comparing to this base. So what we would say is the noise level in the units of decibels, which you've probably heard of before, is 10 times log of I, whatever that intensity is, over I naught. So I'll put this in red because this is really the input. So if we can measure the intensity of a sound, we can get the noise level in decibels using this formula. Okay, so let's do an example using this formula here. Okay, so let's think about this. So a lawnmower has roughly a sound intensity that's been measured at 1.3 watts per centimeter squared. And again, we can pretend that we had some tool that measured this. So my first question is going to be, what is the intensity of sound measured in decibels? Of the lawnmower? Well, we know that the intensity of sound in decibels is equal to 10 times the log of the intensity of the sound over the benchmark. So we know what this value is. That's 10 to the negative 17th or 16th. That is the barely audible sound to humans. And then this is our input for the sound of the lawnmower. And so we can get what that index is in decimals. So we get 10 times log of 1.3, and this is missing something actually. This is not 1.3 watts per centimeter. This is times 10 to the negative 8th. So let's go ahead and let's rewrite that real quick just so we're not confused. So 1.3 times 10 to the negative 8th. So just had a little copying down error there. Per centimeters squared. So a little pop quiz there for you. So yeah, 1.3 times 10 to the negative eighth. So that is your input intensity there. And then the benchmark again is 10 to the negative 16th. So then we can go in and compute this just using a calculator. Okay, so we come in here, so 10, the log button is right here. And then we'll have in brackets 1.3 times 10 to the negative eighth. If yours doesn't have that nice little exponent environment in there, just make sure that you encapsulate the negative 8 in brackets, over 10 to the minus 16. And then close brackets. And so we get 81.14. And again, what are the units here? Decibels. So this is how loud my lawnmower would be in decibels, around 81 decibels. Again, so we can take the given sound intensity, assuming we have this measurement, and map it to that decibel sound. So we can compare that to, right, like a rough conversation in just a small room is about 60 decibels. A rock concert's around like 120. So it's, kind of somewhere in between there. So let's look at another question. We'll keep this lawnmower in play here. How much louder is Ari, my dog? How much louder is her bark compared to the lawnmower? So we know that a dog's bark is around 90. I would say Ari's is probably like 190, but we'll keep it at 90 to be more reasonable. So a dog bark is around 90 decibels of sound intensity. So what we can do is compare the intensities of the sound. Compare the intensities of the sound of 90 decibels versus 81 decibels. But since this is an index, it's not clear what that really means. If I want to compare this in like how many times louder is Ari's bark than the lawnmower? So if we want to compare the intensities, we have to get inside the logs, and we don't know what those intensities were in watts per centimeter squared, right? So what we can do is we know that the lawnmower, that sound, if I subtract that from Ari's sound, this would give me the difference in the two sounds. And we know that Ari's was 90 decibels. The lawnmower was 81.14 decibels. And for Ari, it was really, if we use the formula, we'll use I sub A for Ari over that benchmark, ended up being 90. I'm just going to re-represent it like this, minus the lawnmower, which would be 10 times the log of I sub L for lawnmower. And that equals this difference over here, which we know, right, must be the difference of the two in decibels. So that would be 90 minus 81.14, which should be 8.86. Let me just double check that. 90. Correct. So we got 8.86 should be this difference here in decibels. Okay, why am I doing this? Again, I want to get to a place where I can compare these two. I'm showing you a method on how to do that. So right away we can do something nice, which would be to divide both sides of the equation by 10. If I factor out a 10 on the left, right, and I'm left with log of I sub a over I sub o minus log I sub l over I sub o. And then I divide, or I factor out a 10 here, we can cancel out a factor of 10. Again, the reason I'm doing this is so that I can combine, hopefully, what's going on in here. So we have the difference of two logs. I can use that property of logarithms to rewrite this as, now, right, instead of log a minus log b, I'm going to rewrite this as log of a over b. Hopefully get some nice stuff to cancel. So this is a, this is b. So I get I sub a over I sub o, all divided by I sub l over I sub o. Let me write that a little bit differently. And this all equals 0.886 decibels. And now, if we take care of the inside here, a little bit of side work for those of us who maybe still have a little bit of trouble with fractions. I sub a over I sub o divided by I sub l over I sub o. It's really multiplying by the reciprocal. So what we get is I sub a over I sub l. So RE's intensity over the lawnmower. So this becomes the log of I sub a over I sub o. And this equals 0.886. And then I can raise both sides to as powers of 10, like we've done before, to remove this log. So then I'll just be left with, on the left, I sub a, RE's intensity over the, oh, this should be I sub L here, right? I'm just going a little fast. I sub a over I sub L, not O, because we're comparing RE to the lawnmower. Though the O's canceled, that benchmark sound. Okay, so continuing on, this equals 0.886 as a power of 10. So we come in here, 10 to the 0.886, 7.69. So RE's intensity compared to the intensity of the lawnmower is 7.69. So what does this mean? This means that RE, bless her soul, is 7.69 times louder than a lawnmower. And that I have no trouble believing. And if you've heard her in some of these videos, you would agree. But this is how we can compare these two things. Again, when the range is so huge, you need to use logs to be able to shrink it down, and we need to use ratios to compare them, because just taking an actual difference of the two wouldn't make sense, right? It'd be like saying, let's compare the difference between my salary and Bill Gates' salary. It wouldn't be meaningful to just say, okay, whatever a professor's salary is subtracted from, $90 billion. That's not going to show us as much as maybe a ratio would. How many times or how many Professor Malleys would it take to be working to add up to one Bill Gates? It's a sad thought. But you can tell that ratios have some value in comparison, and logs are the way to access that through breaking down the huge, huge ranges of values. So I'm going to stop us there. We've gone through a lot of big ideas. Again, to recap, we went through the shape and properties of the graph of log functions. A lot of good stuff there, including limit notation, talking about concavity, all key ideas. Hint, hint, nudge, nudge. And then some logarithm applications. So things that have huge differences in value, like pH or acidity and sound intensity, we can use logs to go back and forth between those indexes and the actual values being measured, and then also come up with ratios of comparison. Okay, so hope you find this interesting, and again, I'll see you in the class discussion. Have fun.